Hello, this is the Boiler Exams, Physics 172, Exam 1 2010 Fall Practice. Getting into it, question 1. For the next 4 problems, consider vectors in the diagram shown below, in which each division is equal to 1 meter. What are the components of vector A? So, to find the components, we just look at the change in the x direction and the change in the y direction from the base of the vector and the tip of the vector. So, right here is our vector A. It goes 1 over to the left and, 8 up. So, then in the x direction, our x component will be -1, because we want 1 meter to the left. And in the y direction, the component will be +8, because we want 8 meters up. So, our answer is C. Problem 2. What is the magnitude of vector A? So, in order to calculate the magnitude of a vector, it is the same thing as calculating the length of a vector, calculating the length of this line. The equation is square root of the x component plus square root of the y component. If this was in 3 dimensions, we'd add in the z component squared, then add to the other two, all under the radical. So in this case, magnitude equals 1 plus 64 square root 65 meters, which is approximately 8.06, I think. Just a little bit more than the square root of 64, which is 8. Yeah. The answer is A. Then problem 3. Which of the following statements is true about vectors A, B, C, and D? Then we have a bunch of equations. There's a couple of ways you could do this. You could try to reason it out geometrically. For example, if you look at this first one, all 4 vectors added together equals 0. If that were true, then if you put each of these 4 vectors tip to tail, then you would end up at the same place as where you started, because when you add 2 vectors, it is the same thing as putting them tip to tail, and then looking at where that ends you up. So, in this case, I don't think it would work. I think A would be false. The other way you could do this besides geometrically is you could just calculate what each vector is in its x and y components, and then just manually calculate what each of these equations are. So, I think that way would be the simplest and least prone to error. So, we already calculated A, it's -1/8. B is going to be -7 minus 1. That's this. Goes 1 meter down, 7 meters to the left. C is -1, 4. And then D, it's not a great D. D is 7 minus 3. Alright, so A plus B plus C plus D would be -1 plus -7 plus -1 plus 7. That'll be -2. And then 8 minus 1, 7. Plus 4 is 11. Minus 3 is 8. So A is false. B is A plus B is equal to C plus D. This gives us, let's see, A plus B is -8, 7. C plus D is 6, 1. So it's evidently not true. B is wrong. C is A plus C equals B, which then gives us A plus C is minus 212, and B is minus 7, minus 1. So C is false. Right, hold on. I made a mistake in B. That's a negative. It's my bad. In that case, C minus D. C is minus 1. I guess it's minus 8. And then 4 minus negative 3 is 7. Oh, so then actually our answer is B. It's my bad. And then I guess we'll just calculate the other two for fun. A is equal to C plus B. This gives us minus 1, 8 is equal to C plus B would be minus 8, 3. And then it's also obviously false. Last one, A minus B equals C, which gives us minus 1 minus negative 7, 6, and then 9 is equal to minus 1, 4. So we can see B is the only expression that is true. Alright, problems 4 and 5. A tennis ball of mass 57 grams is served in horizontal direction along the x-axis and initially flies at speed 60 miles per hour. What is the initial magnitude of its momentum? So, in order to calculate momentum, it's equal to mass times velocity. And then since we only want the magnitude, we don't have to worry about the vector components of velocity and momentum. We can just take the direct speed, the magnitude of velocity, and multiply that by the mass in order to calculate the magnitude of the momentum. So, if we plug in our numbers, it's 57 grams. Don't forget to convert that to kilograms. And then our speed is 60 miles per hour. We need to convert to meters per second. It's actually a very annoying conversion, huh? Let's see. So 1 mile is equal to 50 to 80 feet, I think. Yes. And then 1 foot is equal to 12 inches. 1 inch is about 2.54 centimeters. 1 centimeter is 100 meters. So multiply all those together, you get what? Some number. And then this is miles per hour. We have to convert the hours to seconds. 1 hour, there's 3,600 seconds. Alright, I'm just going to directly calculate this and convert from miles per hour to meters per second. So 60 divided by 5280, or multiplied by 5280, times 12 times 2.54. I wrote this down wrong, I'm realizing. 1 meter is equal to 100 centimeters. And then 1 hour is 3,600 seconds, so we have to divide by 3,600. And I got, I'm going to rewrite this over. that the velocity is equal to 26.8 meters per second. So then, our momentum is equal to 54 grams over 1,000 grams per kilogram times 26.8 meters per second, which then gives us 1.44 kilogram meters per second. So, our answer is approximately B, 1.5. Alright, next question. What is the magnitude of the x component of the tennis ball after 1 second? Gravitational force on the ball is downwards in the minus c direction. So in order to calculate the change in the momentum, we're going to use the momentum principle, which is the change in momentum is equal to the force. If we look back at our tennis ball, we're told the gravitational force is acting in the minus c direction. So we're going to have the weight force, and that's actually the only force we have. There's no friction, there's no drag, there's no normal force. We're not told about any of that. So the force of weight is the only force, and so that's going to be the only thing affecting our momentum. However, if you think about it, it's asking us for the x component, and the force is in the z direction. So if the force is in the z direction, but we only care about the x component of the momentum, well, the x component of the momentum isn't going to be changed by this weight force. It's going to remain completely constant. And then, alongside that, when we calculated the momentum in question 4, the velocity is only in the x direction. So the momentum we calculated is the same thing as the momentum in the x direction, because that's the only component of velocity that we have. There is no z or y component of velocity. So what that means is our answer for problem 5 is actually the same thing, because the x component of the momentum hasn't changed. Alright, problem 6. An electron was accelerated to from a speed of 0.9999c to 0.9999c in 1 second. What was the average force applied to an electron during that second? Assume unidirectional motion. The mass of an electron is 9 times 10 to the minus 31 kilograms. So, first thing to realize is that these are very fast speeds. They're actually very, very close to the speed of light, which means we need to factor in relativity. We want to know the average force applied to the electron, and we're given the speed, the mass, and the change in time. So it's reasonable to think that we would use momentum for this problem. If you remember, change in momentum is equal to the force applied. And since we're only worried about the average force, we can write this as the just absolute change in momentum over the change in time is equal to the average force. So then, we know how to calculate the change in momentum, and we're given the change in time, so we just have to plug those into this expression and we can find the average force. So, in relativity, momentum is equal to mass times velocity times the Lorentz factor. If we want to know the change in momentum, that's just going to be everything as before, but with the change in velocity. So, if we plug all this in, we just want to know the magnitude. We don't need to worry about the direction. So I'm going to leave all of this without vector components. Calculate it. The Lorentz factor is 1 over the square root of 1 minus v over c squared times the mass times the change in velocity. I'm sorry, hold on. This doesn't work actually in relativity. We have to write this like this. Now let's do final minus initial. So then, this is just how you calculate any change, final minus initial. So then, our change in momentum is equal to the mass times the final velocity over the square root of 1 minus v over c squared minus mvi over 1 minus v initial over c squared. So, calculate this, we get, running out of space, the mass is 9 times 10 to the minus 31. Speed is 0.99999 c. Don't forget to multiply your c into your speed. C is, it tells us, 3 times 10 to the 8th meters per second. All this over 1 minus Vf over c. Or let me plug in the numbers. 0.99999 c over c squared. This is just the first half of the change momentum. Calculate all of this. You get this is all equal to 6.037 times 10 to the minus 20. And then from this we subtract. That's my dog. Give me a second. Alright, I'm back. So from the number we just calculated, we subtract the second half of our expression. That's 9 times 10 to the minus 31 kilograms times 0.9999 c. Just one less c, because this is the initial velocity, all over square root of 1 minus 0.9999 c over c squared. So, plug this all in, and we get 9 times 10 to the minus 31 times 0.9999 c divided by Lorentz factor, or technically 1 over Lorentz factor. And this gives us 1.909 times 10 to the minus 20. So then our final answer is somewhere around 4.1 times 10 to the minus 20 newtons. Alright, the next question. If an object moves at constant speed, you can irrefutably, having a lot of trouble saying that, irrefutably conclude that the object may be interacting with other objects in the universe, but the net interaction is 0. Alright, so we just have a bunch of conclusions. Alright, well, if we look back at the premise, an object moves at constant speed. We know if the speed is constant, then the acceleration must be 0. And then, from force equals mass times acceleration, if the acceleration is 0, then the force must be 0. Or the net force must be 0. We can still have forces, but the forces must be equal in magnitude and opposite in direction. So that way, the net force is 0, the acceleration is 0. So for example, if you just imagine like a, if you imagine like a block on the ground, it's not moving, so there is no acceleration, but there's still forces. There's the force of weight and the normal force. But since those two forces are equal in magnitude but opposite in direction, the net force is 0, so there's no acceleration going on. So, if we look at our multiple choice answers, we have A, the object may be interacting with other objects in the universe, but the net interaction is 0. It sounds a little bit like what we just outlined over here. When they're saying interaction, they mean like force. So, the object may be interacting with other objects in the universe. It could have forces being applied to it, or it could be applying forces to other objects. But the net interaction, the net force, is 0, which is very similar to what we just outlined, so A tentatively seems like the right answer. If we look at the other multiple choice questions, or multiple choice answers, B, the object does not interact with anything in the universe. This is false, just like the example we put down here. There could still be forces acting on our object, but they just have to cancel out and equal 0. So B is false. C, the net interaction with other objects in the universe may not be 0, but it is constant in time. This is false because it says they may not be 0. The net interaction, the net force, has to be 0 in order for the acceleration to be 0. So C is false. D, the object does not obey the laws of physics. This is just like a filler answer meant to steal your attention. There's nothing in the premise of the problem that implies the situation's impossible. I mean, it's not hard to imagine a situation where you have an object moving at constant speed. So, it's very not true. And then E, there's no gravity acting on that object. Similarly to this example down here, you can have an object with gravity acting on it, so long as there's another force acting in the opposite direction with equal magnitude, and that will produce a situation where an object is moving at constant speed. So, E is false, which means our answer must be A, like we outlined at the beginning. Alright, questions 8 through 10. An object of mass 2 kilograms moves at a constant speed, 0.5 meters per second, along a path as shown. What is the magnitude of the momentum change when the object travels from point A to point B? So, in our graph we have, see point A and point B. The velocity starts in this direction, and then at B it's moved 90 degrees to be in that direction. We're told the speed is constant, so the only thing that's changed is the direction it's pointing, and we want to know the momentum change. So, we know how to calculate momentum. It's mass times velocity. So, change in momentum is going to be equal to mass times final velocity minus mass times the initial velocity. And then we're going to have to do this all in vectors because it's asking for the magnitude. And the magnitude of velocity hasn't changed, but the direction has, which is going to affect the magnitude of the momentum. So, if we go up here, the initial velocity is going to be 0.5 meters per second, all in the positive y direction. So that would look like 0.5 meters per second. And then final velocity is going to be similar, but it's all pointing in the negative x direction. 0.50 meters per second. And then speed is constant, so it makes sense that the magnitude, the overall actual speed, hasn't changed. Calculating change of momentum, get mass, and then final velocity minus initial velocity, or minus 0.50 minus 0.5 meters per second. Oh, there we go. Got the bracket in the right place. So then, momentum change is going to be the mass, which is 2 kilograms, times minus 0.5 minus 0.5 meters per second. Or just minus 1 kilograms per meter per second. So then, you need to delete some stuff to make space. To calculate the magnitude, you just take the magnitude of this vector. So that gives us square root minus 1 squared plus minus 1 squared, which is root 2 kilograms per meter per second. So the answer is E. Alright, next question. Which vector best represents the direction of change in momentum as the object travels from point A to point B? So, first of all, you just have that vector right here. Minus 1, minus 1. So if we draw a little coordinate system, minus 1 would be negative x direction, negative y direction. So down and to the left, which would be E. If you think about that practically, in our diagram, we have velocity first pointing up, then it points left. So, therefore, the change in velocity, and therefore the change in momentum, is going to point down and to the left, just like we calculated. And then problem 10, what is the vector representing the direction of the average net force applied to the object while it traveled from A to B? So, to get the direction of the average net force, if you remember that change of momentum, oh, that's not how you should draw that. Change of momentum over the change of time is equal to the force. So, the direction of the change of momentum is the same thing as the direction of the force. We already found the direction of the change of momentum. That's up here. So, our force is going to be in the same direction, which is E. Problems 11 through 14. 70 kilogram hockey player. I was supposed to say player. Sliding freely on his knees, no friction, on a horizontal icy surface with velocity minus 10.00 meters per second. He then catches a 160-gram puck flying at speed 40.22 meters per second, z-axis vertical. What is the momentum of the player before he catches the puck? Alright, calculate momentum. It is just mass times the velocity. So, this mass is 70 kilograms. Its velocity is minus 10.00 meters per second. So its momentum is minus 700.00. So the answer is A. Problem 12. What is the velocity of the player after he catches the puck? Note that the guy still slides along the horizontal surface of the ice. So, in order to calculate this, we're going to have to use conservation momentum and treat this like a collision. So, what we're going to do is first calculate the momentum of the player and the momentum of the puck before they collide, and then we're going to add together their momentums, and then use that to find their new final velocity. So we already have the momentum of the player, we just need to calculate the momentum of the puck. So it's going to equal its mass times its velocity. Its mass is 160 grams, or 0.16 kilograms, and its velocity is 4022. Or its momentum is equal to, let's see, alright, next we add together the momentum of the player and the momentum of the puck. So that would give us let's see here, minus 700 plus 6.4. Come on. Something like minus 6, 3, or hold on a second, 693.6, and then 3.2.32 kilograms meters per second, and then we divide all this by their combined mass, the mass of the player plus the mass of the puck, and that will give us their velocity. So, velocity together is going to equal their momentum over their mass. Their total mass is 70 kilograms plus 0.6 kilograms. So, that's going to give us minus 693.6 divided by 70.16 minus 9.89, and then small numbers for the other two components. And then, one last detail, we are told that the player is still sliding along the horizontal surface of the ice, so the vertical component of the speed must be 0, otherwise he'd be sinking into the ice or floating above it. And so our z component must be 0. So A is wrong, C is wrong, and D is wrong, because they don't have a 0 z component. And then, our answer is B. Problem 13. What is the change in momentum of a guy? So in order to calculate change in momentum, we need the initial momentum and the final momentum. The initial momentum is easy. We already had that calculated right up here. And so, all we need is the final momentum. You might want to use this value right here for the final momentum, but you have to be careful, because this is the final momentum of the player and the puck. In order to get just momentum of the player, we have to multiply that momentum by the ratio of the mass the player has compared to the total player plus puck system. So, first let me just copy down the initial momentum, and then the final momentum. That's going to be equal to momentum of the puck and the player. I'm going to call that P net, and then multiply that by the ratio of the mass of the entire system to just the player. So mass of the player over the net mass. This gives us minus 693.6, 3.2.32 millimeters per second, and then multiply that by 70 kilograms over 70.16 kilograms, running out of space. So, calculate this. We get minus 692, and then approximately 3.2.32. This value right here, almost all the mass is in the player, so it's going to be really similar. Alright, so there's our initial momentum and our final momentum. So our change of momentum is just going to be final minus initial, which is going to equal around minus 8, or sorry, positive 8. Be careful with your negatives. Positive 8 minus 3.2 minus 0.32. And then a couple of notes. First of all, the player starts on the ground and he ends on the ground. This entire 0.32 right here in the z direction, that's all momentum from the puck that is now gone. I guess when I copy that value over here, I should have made it 0 because the player stays on the ground, so there is no z component of momentum. So this becomes 0, and then I think I messed up the negatives here too. Yeah, I did. Both of those numbers are positive. And so our answer is D. I'm not sure why this is 7.7, our value is 8. I can't figure out why. I'm just going to say it's close enough. And then, problem 14. What is the change in momentum of the puck? So there's two ways you could do this. You could go through the same calculation we did up here, but replace the mass of the player with the mass of the puck. Or you could simply reason it out. All the momentum that the player gained must have come from the puck. So if the player gained 7.7, 3.20 kilogram meters per second momentum, the puck must have lost that amount. So that gives us D. And then notice as a minus 0.32 in the z direction, because the puck started with speed and therefore momentum in the z direction, and then when the player caught it, it lost all of that z momentum. So it's going to have a minus 0.32 there. And that's the entire exam, besides the handwritten part. I think I should do the handwritten part. Yeah, let's do it. Let's do the handwritten part. Starting with problem 1. You see your 10 kilogram bag sitting at rest on the floor at the airport baggage claim, and you rush over to grab it. You jerk the bag off the ground by pulling on it with a constant force of Yeah, let's do it. You see your 10 kilogram bag sitting at rest on the floor of the airport baggage claim, and you rush over to grab it. You jerk the bag off the ground by pulling on it with a constant force of 130 newtons at an angle of 70 degrees above horizontal for 0.1 seconds. The force of your pull is in the xy plane, where the x-axis is parallel with the ground, and the y-axis points straight up in the air. We want to know the velocity of the bag at the end of this 0.1 second period of tugging, and also the total distance through which the bag moved. Alright, so step 1. It says you should define a system. I think we should first just draw a picture. So we have 10 kilogram bag. We're going to call this M for mass, which is what the bag is. And we are jerking the bag with a force of 130 newtons at 70 degrees above horizontal. So that's maybe something like this. This is our force. And this angle is 70 degrees. And then we of course have the force of weight and the normal force. So, what system are we going to use in this problem? I think it makes sense to just have the bag itself be our system, and then the Earth is our surroundings. So, system is the bag, and then our surroundings will be ourselves. I guess I'll write yourself. I don't know. The person grabbing the bag is in our surroundings. And the Earth. And so that means all three of the forces on our right are all external forces. They don't affect the internal energies and all that. List the external objects that interact significantly with the system. Make a carefully labeled diagram showing their interaction with the system. List an object that doesn't interact significantly with the system. We already have our diagram made. It's right here. In this case, the normal force and the force of weight are both interactions with Earth, and our applied force is an interaction with yourself, or whatever you want to call it, the person grabbing the bag. So, objects. The objects that act on our system are, person and Earth. An object that doesn't interact significantly with the system, there's lots of choices you could say. You could say the sun, the air, I don't know, other people in the airport. It doesn't matter. You just can't say one of these two things, or the bag. So, for here, let's say the atmosphere. Use the momentum principle to find the velocity of the bag at the end of the 0.1 second period of time. Show all steps, including units, and circle the final answer. So, want to find the velocity. If you remember, momentum can be used to find velocity, and we can relate momentum to force using the momentum principle, like it mentions. Tablet's not cooperating. So, the momentum principle tells us the change of momentum is equal to the force. We are going to assume that the force we apply to the bag is constant for the 0.1 seconds, which lets us write the change of momentum, or the change in time, is equal to the average force applied to the bag. So, I'm just thinking for a second. Alright, so calculate this average force. It's going to be all three of our forces added together. So average force is going to equal to the weight force plus normal force plus our applied force. And then we have to do this all in vectors because, like they mentioned, they don't want the speed, they want the velocity, which means we have to use vectors, a vector quantity. So then, our average force is going to be the force of weight, which is going to be, negative mass times gravity in the y direction. Normal force is going to be opposed to that. Can't calculate it yet though. And then the applied force, which we need to use some trig in order to calculate what each component is. Just draw a diagram. This is our force. It's 130 newtons. This angle is 70 degrees. So our x component is going to be cosine of 70 degrees times 130. And the y component is going to be sine of 130, or sine of 70 degrees times 130. So did not leave enough space. Now the normal force. So I'm a little bit unsure about how to proceed because if we lift the bag off the ground, the normal force is 0 because it's not in contact with the ground. But if the bag stays in contact with the ground, then we have to calculate the normal force so that way the force in the y direction is 0. Whether or not the bag stays on the ground depends on the force we apply. If our y component of the force is greater than the weight force, there will be no normal force. Otherwise, normal force is scaled so that way in the y direction the net force is 0. So if we just calculate this force in like actual decimals, we get 44.5, and then 122.2. And so we're applying enough force in order to completely lift it off the ground, so there's no normal force, because it's not touching the ground anymore. So we can ignore that. And then from here, we can find the total average force. Just have to add together our two forces. (122.2 minus 98, 24.2). So this is our average force. And then we just have to multiply this by our change in time, and that'll give us the change in momentum. If we divide the change in momentum by the mass of the bag, that'll give us the change in velocity. And since the initial velocity is 0, the change in velocity is the final velocity. So let's do that. Change in momentum is equal to the force times change in time. This gives us, multiply everything by 0.1, 4.45, 2.42. And then the velocity is going to equal to change in velocity, because the initial velocity is 0, which is equal to momentum over the mass. The mass was 10 kilograms, So velocity, come on, it's going to be 0.445, 0.242, approximately. Through what total distance did the bag move during the 0.1 seconds period of time? Show all steps, including units, and circle the final answer. So we're going to do a similar time step thing as with the previous problem, but using velocity instead of momentum. So, position, or distance, the change in distance is equal to velocity. So, similarly, if we assume that the velocity is increasing linearly, we can say change in position over the change in time is equal to the average velocity. So, change in position of the bag is going to be equal to the average velocity times the change in time. The average velocity is going to be the final velocity minus the initial velocity over 2. The initial velocity is 0, so it's just going to be the final velocity over 2. Then times our change in time, which is 0.1 seconds. So we get the change in position is, let's see, and then I think it wants it as a distance, not a vector. So we just have to calculate the magnitude of this vector. Come on. Oh no, that's not what I wanted. That gives us a small number. Around 1/4 of a meter. So that's our answer. Alright, problem 2. As you are walking down a hallway in the physics building, you overhear 2 students discussing a Physics 172 problem in which 2 boxes are being moved across a loading dock. The smaller of the 2 boxes is on top of the larger one. As a worker pushes a larger box, both boxes move together with increasing speed across a level, polished concrete floor. One student says, the worker must be exerting a force on the top box, otherwise its motion would not be changing and it would be left behind as the bottom box moves. The other student responds, no, the worker isn't exerting any significant force on the top box because he isn't in contact with it. The motion of the top box does change though, so it must be interacting significantly with some other object in its surroundings. Starting from fundamental principles, how do you explain the changing motion of the top box in this situation? What objects in its surroundings is the top box interacting significantly with? First of all, let's just draw a picture. We have the ground, and then 2 boxes, with a smaller box on top of the bigger box. Let's just call this M1 and M2. And then we have a worker over here applying some force in the bottom box, like this. We'll say force of, I don't want to use W, because that's also weight. I don't know, let's say A for applied. And then the issue is the top box is moving with the bottom box, but the worker is not touching the top box. So we need to, figure out what's going on from fundamental principles. So, As it mentions, might be a good idea to start by looking at the systems and surroundings of the bottom box and the top box. So, let's say M1, and then over here we'll look at M2. Starting with the bottom box, let's just say the system is the box only, and the surroundings is everything else. That's going to be the worker and top box and the earth. So, we know box 1 is being accelerated to the right by the worker. It's being pushed down by gravity, pushed up by the normal force. So, everything seems to be in order. We'll just say that FA is from the worker. And that's a pretty standard situation. If we look at the top box, we're going to do the same thing. We're going to say the system is M2. Surroundings. Ignore my handwriting. I know it's bad. The worker, M1. Well, I'm going to change something actually. I'm going to put it so M1 and M2 are both in the system always. Here, the force to the right is external because it's being done by the worker. We know M2 is also moving to the right, but the worker is not touching it, and the earth is only moving it in the vertical direction. So these two objects cannot be affecting the top box. So the only other object in our system that can affect the top box is the bottom box. So the motion of the top box is coming from the bottom box. In this case, there'd probably be something like friction that's moving them both together. The top box is moving due to the friction it has with the bottom box, which is being accelerated by the worker. So, that's the solution. So, I think that's the last question. Hope you enjoyed. Goodbye.